Tree cover loss is a global phenomenon that threatens the health and well-being of people and the planet. It can result from natural and human-induced causes such as fires, storms, logging, agriculture, mining, and urbanization. To monitor and understand the dynamics of tree cover loss, it's essential to have accurate and timely data on where, when, and why trees are disappearing. One of the most powerful tools for this purpose is the Sentinel-2 10 meters land use land cover time series, which provides a consistent and comprehensive view of the changes in tree cover across the world in the last few years. So in today's tutorial, you will learn how to use Sentinel-2 10 meters land use land cover time series, how to apply zonal statistics in R to this dataset, and how to create powerful and effective tree cover change maps with R. And welcome back to R, where we will start off our adventure of visualizing a tree cover loss. And the first step is to, of course, install the packages that we need and then load them into our R session. So I like to start off by, first of all, defining libraries that we need. So the first one that we need is the umbrella package tidyverse. And this one we will be using dplyr for data wrangling and ggplot2 for data visualization. The second one is the Terra package, which is going to help us work with raster files. And in this tutorial, raster files are the main focus indeed, because we'll be loading Sentinel-2 10 meters land cover and land use dataset. So we definitely need Terra for this purpose. Because we'll be focused on specific country, in this case Slovenia, but you can also work with any other regions or any other shapefiles, but you would need, in this case, the SF package to do that. So SF package will help you deal with shapefiles. Because we want to calculate the tree cover loss, we'll definitely need to perform zonal statistics in R. And we can either use Terra for that, but in terms of performance, there is another package that does a better job, and it's called extract R. And then finally, in order to get the boundaries of Slovenia, we'll be using rgeo boundaries package. All right, so these are the libraries that we need. The next step is to check if those libraries are already installed. So we're gonna create an object called install libraries, and then we're gonna use this list that we created. And using that list, we're gonna check the row names of installed packages. So this is going to help us determine if they're installed. Now, if they're not installed, we need to install them, of course. So we're going to here write an if-else statement. So if any of installed libraries equals false, in other words, if they're not installed at all, then in this case, we can open this curly brackets and we're just going to say, okay, install packages, but not all packages. So only those among libs that are not among the installed libraries. So that's the trick. All right, and then finally, once we install these packages we just need to load them, and that is quite easy in R. So we are just gonna apply a library function to this libs list that we have, and we're just gonna say here character only. In this tutorial, we'll be doing a zonal statistics of tree cover loss, which means that on the one hand, we need a tree cover raster, and on the other hand, we want to overlay this raster with certain polygons and then calculate the values for those polygons. So in terms of the polygons, I will be using the subnational polygons for Slovenia, but you can also use your own custom shapefiles with polygons for some other units, let's say municipalities or villages or anything else you can imagine. So just for the demonstration purposes, I will be using Slovenia. And for that purpose, I'm going to use rgeo boundaries. And rgeo boundaries has several options here to get different levels. I'm going to go for the administrative level 2. And then you simply need to provide here the ISO 3 code for the country of interest. And I'm just gonna pass this to an object called country SF. So once you actually do this, you should be able to see something like this. In today's tutorial, we'll be mapping a land cover change, or specifically tree cover change, using Sentinel-2 land cover land use data hosted and presented here by Esri on its Living Atlas website. So this is the viewer where you can see this impressive data set at 10 meters resolution, so quite crisp. It is a time series data set, so offers different land cover data sets for different years, starting from 2017 to 2022. In the lower corner, you will see the legends, so what each color represents. And because we are here interested in trees, you can even click here on the trees in the legend, which will only give you then the view of the trees. So how crisp is this data set? It says 10 meters resolution. So if you zoom in, you will see that even though you're zooming in more and more, the level of detail becomes more and more granular. So it's a very impressive one. And in this view, what you can see also is this slider, which allows you to move it back and forth and then see what is the difference in a specific land cover between 2 years. Now, beyond this simply view of this data, it's also possible to download, and this is exactly what we need. So if you go to the lower left corner, you will see a tab called Land Cover. So this is the current view, and then you will see 3 actually icons here just below it. The first one is to download, the second one is to export this to ArcGIS, which we're not going to do, and the third one is about land cover. So if you click about land cover, it's going to take us to a new page, which is going to give you some even more information about this. For what is worth it is we have here several very important things, and one of them is that what it says here is that we should not be using the 2017 year because it has fewer images, or it's based upon fewer images than other years. So this is a very useful piece of information. That's why I actually came to this page, and this means that if I want to compare something, I should start with 2018. So in this tutorial, we'll be comparing tree cover change between 2018 and 2022. That means that we should actually go back and get the data for these 2 years. So I'm interested in Slovenia in this tutorial, and I want to calculate and then map the tree cover change for Slovenia. So going back to this lower left corner and going back to this download icon, this arrow, if we click on it, there will be a new map with tiles opening up, which will allow you actually to download the tile for your specific location. So because we're interested in Slovenia here, we want to download this tile, which is encompassing the entirety of Slovenia. So we just need to click inside of it, and then the new window will pop up showing us what are the possible links that we can download. So because we want 2018 and 2022, you can either click on each of them, which will then initiate a download. But what I will do is I will copy the link address for each of these two, and then I will continue working with them in R. So in other words, I'm going to use R to programmatically download these 2 files on my local drive. All right, our next step is to download those raster files if you haven't already manually downloaded them. So over here, I pasted basically those 2 URLs because I do want to download them through R. They are pretty much the same except for 2 things, which is here LC and then the year. So for 2018, it's of course 2018. For 2022 is a different number. And also here in terms of the date covered. So for 2019, actually what we have here is 2018, complete 2018. So for 1st of January 2018 to the 1st of January 2019. And then for 2022, it's the entire 2022. So from 2022, 1st of January to 2023, 1st of January. All right, now that we have these URLs, we can also pass them to an object which is going to conveniently be called URL. Then we need to pass them as strings in order to be able to download them. So I'm just going to write here, of course, this. So if you already downloaded these files to your local drive, you don't need to follow this step now. I'm doing this only because I want to show you how you can also do it programmatically in R. And now we just need to write a for loop. So for URL in URLs, we are going to open this curly bracket, and then we're going to say download file. So what is the URL? Well, URL equals URL. And then what is the destination file? Well, the destination file should be the base name of the URL. And finally, we want the mode of download to be the binary mode. And once this is done, you simply need to initiate this. Of course, be aware to put the comma here after the first one in this list. So first of all, we define the list of URLs. And once we define the list of URLs, we then just initiate the download. Once we downloaded those two raster files to our local drive, we're finally ready to load them into R and then perform zonal statistics on each of them. So the first thing is to create here a raster files object, which is going to enlist all those TIFF files that exist in this folder. And the folder is located in my main working directory. So that's why I'm saying that the path equals get working directory. And then the pattern here is the TIFF pattern. And finally, but importantly, I want also to include a full pathway to these files. So I'm just gonna run this. And I'm just gonna quickly here increase so that you can see that we have indeed two raster files. One is, and the first one is for 2018, and the second one is for 2022. So the next step is to load them into R and then perform zonal statistics. So the way we were going to do this is using a for loop. So for each of these files, we're going to perform zonal statistics, and then we're going to put them into a single object, which is going to be the list, which will then turn into data frames so that we can easily work with it. So we're going to create here something which is called BD. It's going to be simply just our lists, right? List of these objects. We're going to be storing zonal statistics outputs. Now, the second one is a bit more complicated, so I really would like your attention here. We're going to start off by creating a for loop. So for every raster in that raster files that I showed you, we're going to here open this curly brackets, and then we're going to say, I want to populate this list for every raster that is out there. Simply like this. And then I'm going to open the curly bracket once more. And then within this curly bracket, we can start off by loading these raster files. So I'm going to call this object rasters, plural, because I'm loading two rasters. And then I'm going to use Terra and the Rust option. And then what I'm going to load here? Well, I'm going to load each of the rasters. So that's why I'm putting here raster. All right. So once this is done, we can go ahead and work with our first, or actually work with the zonal statistics. And I'm here going to call this LC, simply length cover. But actually, essentially, we're going to be calculating zonal statistics for trees. So we're going to be doing that using exact extract R and exact extract function from this package. So what do we need to provide here? The first one we need to provide is this object rasters. So this is where those rasters are. The second one is the polygon. So you remember we had this country SF polygon that we provided here. Now, the thing is, if you are not working with lists, which is not the case in our case, you would simply go ahead and, just have here some kind of a function. So maybe you want to calculate average value, maybe mode, maybe median. But in our case, we want to calculate the area size that is under trees. And for that purpose, because we are here having a list of two rasters, we cannot simply just pass here function. We need to provide a custom function here, and then to use that function to calculate whatever we need. So in this case, we're going to go ahead and here create exactly after this one, we're just going to say function, and then function will be function of df, because we're going to be creating a data frame here. And then we're going to open curly brackets once more. And then within this one, we're going to create this data frame. So the data frame is, what is it going to do? Well, it's going to first of all group by those names of those municipalities or those individual polygons on Slovenia. And the column is called shape name. So that's the name in that country SF that gives you the names of them. Of course, we can go also for the numeric identifier, but for now, we're just going to use this one. All right, so this is the first thing that we're going to do once we get the zonal statistic. We're going to group by shape name, and then we're going to summarize. So we're going to again use the plier. So summarize, and then within summarize, we want to measure the area size that is under trees. So we're going to be creating here area, let's say square kilometers, right? And then it's going to be the sum. And it's going to be the sum of coverage area, which is the function from extract, exact extract R. But coverage area not for everything, we want only for trees. So we here need to specify these brackets and say only where value equals 2. In other words, only where the value actually equals trees. And that's not all, because what this function will do, this coverage area in exact extract R, it's going to calculate in square meters, but we want square kilometers. To get square kilometers, we need to divide this by 1 million. Why by 1 million? Because 1000 times 1000 meters equals 1 square kilometer. Why is that? Because 1000 meters equals 1 kilometer. Right? So instead of writing here the full thing, we can just write 1e6, which basically means 1 and then 6 zeros. So this is actually also equals to 1 million. It's a bit strange the way it's done in R, but that's how it is. All right, so now that we have these thingies, our next move is actually to go ahead and turn this into a df. So this is still not a df. So then we turn to this exact extract R, and there is a function here which says summarize underscore df equals true. In other words, whatever you do with the zonal statistics, please put it into a data frame. The second one we also need to emphasize is that coverage area is something that we are calculating here. The other option is to calculate the fractional coverage area. So that will give us percentages. We're not interested in that. We did this in one of the previous tutorials, but in this one, we're particularly interested in the size of the area. So this is why we're including this one. And finally, we also want to include one of the columns from the polygon, which denotes the name of those subdivisional polygons of Slovenia, and that one is called shape name, exactly the one that we used above. All right, and once this is done, what we need to return here is this LC object, which we defined at the very beginning where we actually did the zonal statistics. We now have the output from the zonal statistics in that list called DD, but we want to turn this list into a data frame where we would essentially have 3 columns. The first column would be the name of those subdivision polygons, while the other 2 would be the area size of the trees for each of the years. So to do that, we're going to create a new object called outputs, and then to dissolve this list, we're going to use do call and find the results or the outputs of this column wise. So we're going to be doing it just like this. Once we do that, we can create, let's say, a data frame, which is going to be called tree df, and we're going to be using as data frame and apply to this output. So this is how we do it. And then we can actually inspect how this data frame looks like. We're going to inspect, let's say, just a few first few rows to see if this what we did actually makes any sense. So we actually got here 4 columns. So we have one is, you can see here, shape name, but it also inherited the name of that specific raster file, so 2018. Then we have one which is the area size in kilometers, again for 2018. So this is good to kind of understand where it comes from, but the names are not good, so we need to change that. Then we again have the shape name for the 2022 raster file. So because we did the for loop when we did the zonal statistics. And finally, but also very important, we have also the area size of the trees for 2022. All right, so what we essentially need here is we need the first, second column and the fourth. And we can immediately jump and do that. So we can create, let's say, object called Slovenia 3df. And we can pass this one into a pipe where we're going to be using the plier to select only, so as we said, the first, second, and the fourth column. And we can just apply like this. All right. And then finally, we can also rename these. So I would say that we can keep that old shape name, because we can easily use it to join to that, finally to that country SF object. So this is the first one. We can call this, let's say, tree cover 2018, and then finally we have tree cover 2022. All right, so we also rename this. Once we name, we can also simply, check this newly created or newly modified, I would say, data frame. It's the same one as before. So we can just check here if the changes have indeed taken place. Yes, they did. So now we have the data frame in the shape that we wanted. So as we said, the first column is the name of those municipalities. The second one is the tree cover for 2018, and the third one is the tree cover for 2022. Now that we have tree cover area size for 2018 and for 2022, we are finally ready to calculate tree cover change and determine if really it's all about tree cover loss or there is also some tree cover growth. So we'll be working based on this Slovenia 3df, and we're going to put this into a pipe, and creating new columns is handled by mutate from dplyr. So here I'm going to create tree cover change column, and this one is going to be the percentage change. So we need here a formula for percentage change, which is the following. So first of all, the new value, or the new tree cover, minus the old tree cover, which in this case is 2018, and then divided by, again, the old or the previous, which is tree cover 2018. And because I want percentage change, I'm gonna, and not decimals, I'm going to multiply by 100. And once we do this, we can simply run. And once we run, we can then inspect by using the summary what are actually the values here, and see, how they are positioned. So okay, tree cover change. And then once we run this, we will be able to see the following thing, which is the minimum is 35 almost percentage loss, which is a lot. Median is minus 3.34. A mean is over 4% loss. And then there is, it seems, only one value, which is the increase, almost 3%. So wow, there's a lot of tree loss in Slovenia. All right, so once we have the data frame, in order for us to easily plot things, we would need to merge this data frame back or together with that shapefile, which is called country SF. And that's going to be pretty easy. So let's create a new object, which is going to be Slovenia tree cover change. And because zonal statistics does not really change the order of rows that exists over the country SF, so the order of rows is the same here in the Slovenia 3df and country SF, means we can just merge them column-wise using cbind from base R. So it's that easy. So country SF here, and then also we can use the Slovenia 3df. And once we run this, it's going to be merged. So the next step then is to finally start creating our map of tree cover change. All right, folks, we are ready to map our tree cover change for Slovenia. So let's create an object called map. Let's call ggplots. And then let's use geom_sf. We're using geom_sf because our main object, Slovenia tree cover change, is an SF object. So we need to follow that. So we then determine, or we say that data equals to Slovenia tree cover change. And then our main aesthetic here is going to be the fill aesthetic. So we want to fill those polygons. And the variable for that is tree cover change. All right, so for the simplicity's sake, maybe we don't want to put any borders, but perhaps in this case would not be a bad idea so that we can actually see what's going on. So we can use, for example, let's say, well, let's use the white one, white boundaries of those subnational units. And let's, for example, choose 0.15, so not that thick. All right, once this is done, we are ready then to define the colors. So here we're going to be using continuous color scale, which means we need to use scale fill gradients. We're using gradient here, and 2. 2 is because we're here having positive and negative values. It's true negative values dominate, but we still have both. We should use actually a palette that is going to account for that. So scale fill gradient 2 allows you to define the lowest, mid, and the highest points. And this is exactly what we need. So let me show you what I mean about that. First of all, let's define the name or the title for our legend. Let's call it here percentage change so that everyone can understand what's going on. Then the midpoint. So the midpoint is, or actually let's first define the midpoint. So midpoint is here going to be 0. Why I'm taking 0? Because 0 is, of course, the middle between the positive and negative values. Of course, in our case, negative values, they dominate. So a midpoint in reality is not really 0, but I want to set 0 here because I want the colors to correspond to either positive or negative values. Now, about the positive or negative values. So the midpoint, which is going to be 0, it's actually going to be, I'm going to choose here a yellow color. For the lowest point, I'm going to choose a pink value, and then for the highest point or a positive point, I'm going to choose the green value. So these are color-friendly colors when they're combined. So for this one, I'm going to go again for a yellow palette, which I already predefined. So it's F7BE7C. For the high point, as we said, we want some kind of a green color. So again, I have it predefined 006F00. And then finally, the low points are the negative values. As we said, it's going to be pink, 9, E3, 1, 9, D. Okay, so once we define these things, what we can do next is we can shape the way our legend looks like. And for that, we can use guides. Now, guides, in our case, we are using guides for the fill aesthetic, so we need to define it here. And second, because our legend is based on continuous values, we should use here guide color bar. And then we open the brackets here, and then we can specify things. So one thing that I would like to do here is make it horizontal. The second thing is we can also play with the height and the width of those bars. So bar height would be, you know, how high is it going to be. So I don't want to make it very thick. So I'm going to put it here at 1.5 millimeters. I can also go ahead and define the bar width. The bar width, because here it's a horizontal one, we can go ahead and make it longer, let's say 20 millimeters. We can also specify, let's say, for example, title position. So for the title position, I would like to put it on the top. We can also specify a label position in a very similar way, but it's called label position. Labels can be positioned just below that bar. We can also, for example, specify the horizontal justification. 0.5 means it's going to be in the middle. And we can go ahead and also do the same for the label horizontal justification. And then because we're here using a horizontal legend bar, then the number of rows is going to be equal to 1. And then I also want to put them next to each other, those values. Okay, the final thing is defining the theme. I'm not going to overcomplicate this time. So first of all, I'm going to be using theme void, which means I'm going to get rid of any excess material. or any excess things around it. And then I'm also going to specify here theme itself, because I do want to customize some more things. And one of the things I want to customize is the legend position. I would like to put my legend at the top of this map, so just above the map. And then the final thing to also define here in the theme is plot margin, because I want to keep my space around the map fixed. So plot margin, here we need to specify for all the 4 sides of the plots that it's going to be equal to 0, which means we don't want to expand it or shrink it. So top and bottom side, then also the right hand side, and finally the left hand side. And here we simply also need to specify what are the units that we're gonna use. And here it is, the tree cover change map for Slovenia between 2018 and 2022 using Sentinel-2 data from the Living Atlas of Esri. So here we go. We have actually a map which is mostly in pink and yellow colors. This is because for most of these places in Slovenia, for most of these units, there has been a tree cover loss in the last 4 years, which is very sad. So we don't really happen to see almost like any tree cover expansion, which would be a clear green color. So it's either stagnation or tree cover loss. And that's all for today, folks. In today's tutorial, we used Sentinel-2 land cover land use data, and then through the zonal statistics in R, we analyzed what was the tree cover change for different Slovenian sub-units. I'm really curious how you can take this tutorial on a journey across the world and do your own analysis and produce some cool maps on tree cover change. If, however, you would like to replicate today's analysis, I've prepared a GitHub repo in the description box below. So go ahead, check it out, clone it, reuse it, modify it as you see fit. If you have any questions, comments, or just general feedback, feel free to reach out to me here on YouTube, but also on X and Instagram. If you're new to R and you seek to expand your data visualization and geospatial knowledge in R, I've prepared a few cool tutorials for you. See you next time.